Hello, everyone, and welcome to the webinar on Brownian Motion in Excel. Now, before we jump into the topic, I just wanted to mention that Peaks to Tails is coming up with this new course called as Deep Quant Finance. So essentially, it's the quant finance, as you know already. If you don't know what quant finance is, perhaps you have heard of financial engineering, right? So it deals with pretty primarily the derivative valuation landscape and risk management. So using all the analytical ideas as well as computational finance, which deals with numerical techniques to price derivatives and do risk management, also trading as well. So in deep quant finance, we will be covering the entire derivative valuation landscape, all theoretical ideas, as well as numerical techniques that are used. Plus, there is a module on quantitative portfolio management. Okay, so how do you go about using statistical models to create investable portfolios for different clients? That is one topic that we have added. And throughout the course, the focus would be programming in Python. And of course, the main topics will be supported via Excel examples as well. So you'll have Excel as supporting materials, but the focus will be on coding in Python. Okay. And the other thing is, throughout the course, there will be a basically the machine learning and artificial intelligence will be like an overlay uh, on the entire course. So we will see how the different machine learning algorithms are impacting the financial engineering landscape today. So that's why the name deep. Deep is coming from the deep learning, and then we have quant finance, right? So that's at a very high level what the course is all about, and we are starting the live batch in April, right? If you want to learn more about the course, the syllabus, the logistics, and fees, etc., please visit the website peakstotales.com, or feel free to reach out. You can call or email also. All right. So yeah, if you're more interested, about this particular course, then after this webinar, you can reach out. All right. That being said, um, today's topic is Brownian motion in Excel, right? And in layman's term, it is understood as a drunkard's walk. Okay. Now, why is this relevant? All right. First of all, this particular topic is maths intensive, but in this webinar, I will try to keep the maths to the minimum. Okay. Today is all about having fun. So we'll have there are plenty of cool animations that I'll show you that will help you understand this particular topic. And I'll keep maths to the minimum as much as possible, right? Now, let me explain the role of Brownian motion in quant finance. Um, the role of Brownian motion in quant finance is like the same role that probably salt plays in the recipe. Okay, Brownian motion to quant finance is like salt to recipe. It's that important. I'm not exaggerating. Brownian motion sits at the heart of quant finance. Okay, all the modern day financial engineering applications that you have today, for example, pricing, risk management, trading, etc., probably the first equation that you write, right? That involves Brownian motion. The first equation that you write that involves Brownian motion. Popular example, Black-Scholes. Well, if you look at Black-Scholes equation, the PDE as well as the final solution, whenever you derive the Black-Scholes, right, the first equation that you write that involves, how stock price evolves, right? That involves Brownian motion. Okay, so it's the starting point of all of quant finance. That's why this topic is extremely important. Now, this topic is rigorously treated under a study called as stochastic calculus. All right. So financial engineering courses everywhere have this topic called stochastic calculus. Now, in this course, you will be grilled thoroughly on stochastic calculus so that you are extremely comfortable, handling the equations and then coding them. Right. So that will be the focus of the course. Okay, so that being said, let's get started. All right. Now, okay, so as scientists, right? As scientists, we have the propensity to model everything or write down equations for everything that you see in the universe. We don't like uncertainty. We like to put some equations that describes the dynamics of moving things, correct? So if you are from an engineering background, or let's say you have studied this in physics, if you're familiar with this particular motion, it's called a projectile motion. Anything that you throw in the air follows a particular trajectory, right? We call that a projectile motion, and the path is completely governed by this equation, right? So we have an equation that defines the trajectory of how the ball or a particle that you throw in the air will follow. Now, the thing is, if you keep the velocity, initial velocity same and the angle same, every single time it follows the same path, right? So that's powerful. I mean, you have written down an equation and you know exactly at what point, where it will be at, after how much time. So you can completely describe this path. That is beautiful. Yeah, thanks to the equation, now, countries can throw missiles at each other with precision, right? Another example, if you look at the motion of planets around the sun, that also is governed by an equation, right? Planets revolve around the sun in an elliptical orbit, and this is the equation. Don't worry about all these terms. I'm just saying that when it comes to physics, we have equations that describe the motions of moving particles, and they are pretty much deterministic. That means you can exactly pinpoint where a particle would be at a given point in time. When it comes to finance, though, look at a stock price evolution. This is how a stock price looks like. I think I took it from this is IBM data probably. Last one day, the stock price has evolved like this. If you look at over the last 5 days, it has evolved like this. And if you look at 1 year, this is the path. Now, the biggest difference is there is a lot of randomness or uncertainty in the evolution of stock price. It does not behave anything like all these physical particles, right? So the question is, what do we do about it? Because as scientists, right, we don't like uncertainty. We need to put some equations that describe the motion of, or in our case, the evolution of stock price. Doesn't have to be stock price. It could be interest rate. It could be exchange rate. Could be commodity prices. Any underlying financial risk factor, right? We want to put some equations that govern the dynamics of these underlying variables. All right. So how do we go about it? Well, first question, can we perfectly predict what the stock price would be maybe tomorrow? Feel free to write your answer in the chat box, and let's make this interactive. Can you perfectly predict the closing stock price tomorrow? That nobody can. Nobody can, right? Otherwise, the entire trading industry would not even exist. So it is completely random, yes, but can you at least do something about it? See, there is a key difference between perfect predictability versus modeling. Perfect predictability would be something like this. You put down an equation, there is no randomness, nothing. It gives you an exact answer where it will be, right? In this case, we can't perfectly predict, but we can model. Modeling means what? Modeling means you specify a distribution. Don't tell me exactly where the stock price is. That is fine. At least you give me a distribution so that I know, okay, this is the mean, this is the variance, this is how uncertain it will be, and on an average, where it will land, right? At least give me a distribution. So when you specify the dynamics using a distribution, it's called as modeling. Okay, so all we need to do is devise an equation that has some kind of randomness in it. Okay, these two equations do not have any randomness, it is exact. But in case of stock price, we have to create an equation that has built-in randomness in it. Okay, maybe then we can do some justice to this evolution. And that's where Brownian motion comes into picture. Okay, so if I were to tell you that Brownian motion is like the fundamental currency of randomness. Okay, anything that is random, you want to model that, you use Brownian motion. It's the core atomic unit that gives you randomness. Okay, so that's the introduction, and we'll see how this works. Okay, let's start with a very simple process. We will try to model random behavior. Okay. All right. So the first process that we'll look at is called a simple symmetric random walk process. Now, again, as I promised, I'll keep the maths to the minimum. Today, just enjoy the session. There'll be a little bit of maths for our understanding and a lot of cool animations, as I promised. Okay, so let's understand this. Consider a variable x, okay, which only takes two values, +1, -1, equal probabilities. Okay, that's why it is called symmetric, equal probabilities, +1 or -1. Now, this is a step. If you take one step, right, you could either, it can be either +1 or -1 with equal probabilities. That's the step. We can easily calculate the mean and variance. Expectation of the step is simply 0.5 times 1 plus 0.5 times -1, that is 0. Okay, so on an average, the step will take a value of 0, although it never takes a value of 0. It is either +1 or -1, but on an average, since it is symmetric, right, the mean of the step is 0. Variance you can also calculate, easy. Variance is 1. Okay, so that's the mean and variance of a step. Now, let's talk about a walk. What is a walk? A walk is sum of steps, right? This is just a sequence of steps. So you add all the steps together, you get a walk. So define y as a walk, which is nothing but sum of n steps, as you can see, right? Nothing fancy. Now, it is not just n steps, it is sum of IID steps. What does IID stand for? Anyone, quickly? Sum of IID steps. What does IID stand for? Independent and identical distribution. Correct. That is correct. So IID means every step will follow this distribution. That is independent. Identical. Identical means every step will have the same distribution. 0.5 probability for +1, 0.5 probability for -1. That's why identical. Independent means no step is dependent on any other step. Okay, the future step that you'll take does not depend on what kind of steps you took before. So every step becomes independent. There is no correlation. Okay, that's the assumption. Now, having said that, what is the expectation and variance? Easy. Expectation of the walk would be the sum of expectation of each of the step. And you get a bunch of zeros, you add them, you get a 0. Okay. So the average value of the walk is 0. That means after n steps, n is arbitrary, it could be anything. On an average, you are still supposed to be there where you started from, as if you have never moved. Okay. So expectation of the walk is 0. That means that on an average, you're expected to be exactly where you started from. What is the variance? Variance of the walk would be sum of individual variances. Why? There is no covariance term because it is independent. Steps are independent, so you just add all the variances, you get the total variance. Each variance is 1. So total n, there are n steps, so overall variance would be n. Okay. Okay, so we got mean of a walk is 0 and variance of the walk is n, which is equal to the number of steps. If you take sufficient number of steps, sufficiently large number of steps, n tends to infinity, then magically you can impose this normal distribution. In these two equations, I have not imposed any distribution, just the expectation and variance. But if you take large number of steps, thanks to central limit theorem, you can say that y follows normal distribution. Mean and variance you already calculated. So that remains as is. That's the theory. Okay. I hope this is, you're all comfortable with whatever we have done so far. The maths will not get more complicated than this. We are just going to deal with expectation, variance, that's all. Any questions, let me know. If you are clear, let's look at an animation. Okay, all right. So what I have done here is, this is the number of steps I am tracking. And for each step, what is the value of the step size? It could be +1 or -1. That I am modeling using a random number. Okay, so the probability of up movement is 0.5. Probability of down movement is also 0.5. So I'm just using Excel rand function to check if it is less than P, then +1. If it is higher than P, -1. So they are equally probable. So I'm taking random steps at different different number. And for the walk is nothing but just a running sum of the steps, correct? It's just a running sum of all the steps till that point. Okay, simple stuff. Now, the question is, after one step, let's take it slowly, okay? And then we'll speed up. After one step, n equal to 1, what are the possible values of y? After one step, see, y is the walk, okay? After one step, what would be the possible values of y? One or -1. Exactly. If it is just one step, right, then this walk becomes that step. There are no other steps. It's just one step. Since the step has two values, +1, -1, y can also have only two values. Okay. So you can see here there is a very small arrow here that shows what is the value of y after one step. Right now it is -1. You can see this is -1, correct? If I press F9, now it became 1. Sometimes -1, sometimes 1, right? These are the two values. Probably, what are the probabilities? Associated probabilities? So some of you are saying 0. See, 0 is on an average. Please remember, very important. The values that it can take is +1, -1. But on an average, it will be 0 because both are equally likely. Okay, you'll never see the value of 0 in one step. All right. I hope that is clear. Yes, so they are equally probable. Okay. That is correct. Now, what happens after two steps? If I make n equal to 2, after two steps here, what are the values of the walk after two steps? Possible values of the walk after two steps. Zero, 2, -2. Interesting. 0, 1, 2, -2. Okay. Good. I'm getting a mixed set of answers. Yeah, right. So see, there are only a few combinations. Either it can be +1, +1, which is 2, or -1, -1, which is -2, or +1, -1, which is 0, or -1 +1, which is 0. So three possible values, three discrete possible values: +2, 0, -2. Everybody agrees? All of you comfortable? After two steps, the possible values would be +2, 0, -2. Only those three values. It is still a discrete random variable. It is not continuous because these are the only three possible values. Now tell me one more thing. Are those three values equally likely? Same probability, or one of them is higher? Zero is higher. Are you sure? Everybody agrees zero has higher probability? Okay. Okay. Yes. Yeah. That is completely common sense, right? Um, can you tell me the probabilities? What is the probability of +2? It's just an easy mental count. 25%. Excellent. What is the probability of -2? 25%. What is the probability of 0? Obviously, everything has to add up to 1, so 50% exactly. It is higher for 0 because there are two combinations. +1 -1 also leads to 0. -1 +1 also leads to 0. So there are two possibilities. Okay. So after two steps, let's see the, oh, before that, I have drawn a histogram of y. So histogram actually shows you the distribution. Remember what we said about modelability. If you want to model a process, essentially you are trying to come up with a distribution that describes how it will behave. Distribution packs a lot of things. Distribution gives you the average. That means on an average where the location would be. Distribution also gives you variance. That means it tells you how much uncertain it will be. Okay. And a lot of other moments also you can calculate. This is the histogram. You can see after one step, either it is +1 or -1 and almost equally probable. I'm creating this by doing a lot of simulations behind the scenes. You don't have to worry about that. This is a sampling distribution. Okay, it's not a theoretical distribution. If we do a theoretical distribution, it will be exactly the same size, right? Okay, after two steps, let's see. If I increase the steps, you see it took a -1 and a +1. So overall, the value of the walk is 0. That is what you see in the diagram, right? I can do multiple random simulations. So now it is +1, -1 again. This time it is -1, -1. You can see -1, -1, leading to -2. Okay. What is the distribution? This is the distribution. At 2, we have, this is actually frequency plot. It is not the true probability mass function. But you can get an idea which is more likely, which is not, right? So at 0, you see the probability is double. Right? I hope this is clear. Now, what if I increase the number of steps? Let's increase it to 50. Or you give me a number. Give me a number between 1 to 100, any number. I'll take the first suggestion, 30. Okay, let's take 30. After 30 steps, we have this particular path. This is one of the possible realizations, right? If I press F9, I'll get another path. Correct. After 30 steps, what are the possible values of y? Well, there is a lot of possible values, so don't worry about it. But anyways, we have a histogram here. These are all the possible values and the corresponding frequency. All right. Now, what do you see about this particular histogram? How is it looking like? It is starting to look like a normal distribution. And we are not surprised. We are not surprised because the central limit theorem says if you increase the number of steps to a sufficiently large extent, the distribution will approach normal distribution. And for n equal to 30, we can already see that is happening, right? Let's take probably n equal to 50 maybe. Right now, the value is -10, but this is one of the possible realizations, and we get more and more. Did you notice one thing? You're getting more and more extreme values. Okay, with only two steps, you can only take 3 values. Correct? That's the range. But with higher number of steps, not only it looks like a normal distribution, the values that it can take are becoming more and more extreme. Now it's +20 to -20, right? Okay. By the way, let me ask you this. With n equal to 50, what is the highest possible value it can take? 50, exactly. Correct. And lowest possible value is -50. Excellent. So I hope you understood this entire sheet. Any questions on this? Step, walk, theoretical expectation variance, central limit theorem imposes normal distribution, and we verified everything through animation. Are we clear on this sheet, everybody? Okay, all right. Now, question. After every sheet, I'll ask the same question. Okay, I think probably 5 times. This is the first time I'm asking. Can I use this to model stock price? Well, this is kind of, looks like we got something which is random, and it kind of looks like, maybe looks like a stock price. But can we use it as is in this state to model a stock price? What is the issue with this? What is the issue with this particular process? Okay, trend is missing. Good. Drift missing, going negative. Awesome. All of you are right. All of you are right. So we'll address all these problems and basically enrich this particular process one by one so that it starts to behave like a stock price and we can model stock price. But before going there, there is a fundamental gap in this process and what we want to achieve. The fundamental gap is this particular walk right now is a function of steps. It's a function of n. N is my number of steps. What would I do with number of steps? That is not something I want to address. My questions would be like this. How will the stock price look like after a year? How will the stock price look like after a month or maybe next day? I don't want to answer how will the stock price look like after 50 steps. Steps is vague, right? It's just an arbitrary number. In this model, there is no mention of time anywhere. And time is a fundamental input variable for modeling. You want to know, or your question should be in this form, right? Give me the distribution after 1 year. And then you go with, option pricing and all that stuff. First, you need to bind the distribution as a function of time. Okay, time to evolution. Okay, so that's the fundamental gap. Right now, it's as a function of steps. We want to make it a function of time. Okay, so how do we do that? Well, bring the time element. When you are talking about the step, right, start talking about how much, what is the duration of that step, like how long it will take to take one step. One step takes how much time? Okay, start bringing the time element. Try to tie this process to a time dimension. Accordingly, you can argue how long will the walk take, correct? So things like that, right? So let me go to the second sheet. The next process that we'll discuss this is called scaled symmetric random walk. Okay. Now I have done a few tweaks, just a very few tweaks. So pay attention. First of all, as I said, right, we have to bring in the time dimension. So let's say that our question is this: after time capital T, where is Y? Where is my walk? And how uncertain it will be after a time capital T. Okay. In other words, we are trying to find the distribution of Y at time capital T. That is the fundamental thing that you have to model for any use case. Okay. So I'll do a few tweaks to my process so that it can fit to this particular, or it can address this particular question. So first thing first, I know that total time of evolution is capital T. Okay. So let me divide that time capital T by n number of steps, right? So T by n is delta T. Delta T becomes the duration of a step. Each step takes time, delta T. So n steps will take time, capital T. That is what I want. The entire walk is for time, capital T. Each step is for time delta T. Okay, and delta T is capital T divided by n. That is the first thing. Second, step size. Step size was +1 -1. I cannot retain that, right? Because artificially it will blow up. I can go ahead and make okay, you want to find out the distribution of stock price after 1 year, fine. I will take 200 steps. If each step has +1 or -1 step size, the process would, easily blow up. Okay. I can artificially go ahead and make any number of steps. I can take 1 second as a step, and that will just, the process will explode. So depending on the number of steps that I take, I need to adjust the step size as well so that it is manageable. The overall walk has a specific and a finite distribution. It doesn't blow up. Okay. So what I've done here is the step size has been scaled by square root of delta t. And I'm keeping the signs intact. So 0.5 probability that will take a step of length square root of delta t, and 0.5 probability that will take a step of minus square root of delta t. Now let's see what happens. This choice is not arbitrary. There is purpose behind this. What we get out of this is something that looks very nice. Okay, so let's look at it. What is the expectation of the step? Again, that's very easy. Just, in case of +1, -1, you replace these guys. Again, still this is symmetric. Expectation is 0. On an average, the step takes a value of 0. No issues. Variance formula, if you use, you get delta t. This is very nice. This is nice because every step, right, on an average has a value of 0 and a variance equal to the time step. Equal to the time step. Okay. Couple of questions I'm getting. What is delta t? See, delta t is simply, first of all, what I'm trying to find here is this distribution of the stock price or any underlying process that I'm trying to model after a time capital T. Okay. Now, that is a more natural question. You want to know what does the stock price look like after a year, not after 50 steps. Okay. So that's the first. I can divide that time by n number of steps. That number of steps is up to me. I can think of a weekly evaluation. I can think of a monthly evaluation. Ultimately, I have to cover that 1 year period. But number of steps that I take to cover that period is up to me, right? And so basically delta t is the time taken for one step, right? This choice is elegant. I know how we got there is it is just one of the choices which helps us have a very desirable distribution. I'll show you. I'm coming to that. Okay. First, let's go ahead with the basic mathematics. Did you understand expectation of the step is 0 and the variance is delta t? Simple, same equations, just replace square root of delta t in place of +1 -1. I hope this is clear. Okay. Now, the expectation is 0, variance is delta t, which is the time interval, or you can say time step, delta t. Okay. More number of steps you choose, delta t will get smaller and smaller and smaller, right? Because it is capital T by N, T is fixed. Let's say T is 1 year. Capital T is 1 year. Number of steps I can change. Right. Now, what happens to the walk? Same equations. The expectation is again 0, right? On an average, the walk is supposed to be exactly where you started from. But look at the variance. Variance of the walk is sum of variance of individual steps. But the variance of each step is now delta t. So what is n times delta t? We get back the capital T. We get back the capital T. This is the time of evolution, which is part of our question or we are interested in, right? So we came up with a process. Okay, let me complete this also. Now you impose central limit theorem. So you increase the number of steps and that will bring in this guy. It will impose normal distribution. Expectation variance we already calculated. So with large number of steps, our random walk will follow normal distribution. But the key difference here is now the variance is equal to T, not number of steps. Now this is desirable. Okay, so to answer your question, we created a process, okay, which is random because it is normal distribution, but has a variance which is tied to our choice of time variable in the simplest way possible. Variance is equal to T. Okay, so that is desirable. Now we could create a process that is tied to the time dimension directly, not steps. You can divide it into as many number of steps as you want. This remains intact. There is no change to this because if you change n, delta t also gets changed. Step sizes also get impacted, but the overall effect is the same normal distribution, zero mean, variance equal to capital T. Okay. And from a modeling standpoint, this n would be like, let's say we want to do a weekly evolution in 1 year. So you will divide it into 52 steps. You want to do a monthly evolution. Your number of steps would be 12 for a year. You want to do a daily evolution. Your number of steps would be 252. Accordingly, your delta t gets impacted, your step size gets impacted, but the overall effect is still tied to that 1 year. Okay, t. Right? So this is definitely much more useful than what we had before. Now we have things naturally linked to the variable of interest, which is our time of evolution. Okay. So let's do the animation for the same. So here, what I'm doing is based on number of steps, right? Obviously, the delta t would be total time capital T divided by n. Right now, everything is 1, so this is 1. I can change the number of steps, right? Doesn't matter. Delta t will keep changing. The step size will change. Now see the tweak I did here is this +1 -1, which was random. I multiplied the square root of delta t because that is now my new definition of step. Either it could be plus square root of delta t or minus square root of delta t. That is what I'm modeling in the step column. Walk is again a running sum of steps. Nothing has changed. All right. Okay. Now you see this green cell here. I am using this to signify at what time capital T I am interested um, to see where the walk has landed. Okay. Right now I'm focusing only on what happens after a year. All right. How do you get there? Whether 2 steps, 3 steps, 200 steps, that is part of the modeling exercise. It really does not matter. Okay, so I'll keep capital T equal to 1 fixed. I'll change the number of steps. Okay, right now it is just 1 step. I'm going from 0 to 1 year in one single jump, 1 step. Okay, and the walk again, yeah, the walk can be either +1 or -1 because if you keep delta t as if you keep t as 1 and n as 1, delta t is also 1, and this actually becomes this again simple symmetric random walk. But I will change n. Okay, so you can see here on the x-axis I have the time capital T. From 0 to 1 time capital T equal to 1, I'm going in one shot, one jump. And the value of the walk can be either +1 or -1. That is exactly what we see here. And on the right hand side, you have the histogram. Again, yeah, this is Excel's default histogram, but you know very well, this is either at the moment -1 or +1. These are the two possible values after one step, right? Now let me increase the number of steps. When I make n equal to 2, my green mark moves down. It is always at time capital T equal to 1 because that is what I am interested in. I want to find out the final value of the walk after time T capital T equal to 1. Right now it is this. You see everything got changed. Now my step size has become, what is delta T first of all? Delta T is 1 divided by 2, right? Square root of delta T is 1 divided by square root of 2. 1 by square root of 2 is a number that you should remember. It is 0.707. Remember that will be helpful. So in one step, you can take this value, right? Plus this or minus this. And in 2 steps, obviously, the 4 different combinations are possible. But ultimately, your walk will have the same 3 different values, and this is the histogram. Exactly something similar that we had in the simple symmetric random walk, but the values would be different because your step size are different. Okay. Yeah. Now let me draw another path. Oh, it is again both positive. That's why you're seeing this line. I'm trying to see one positive, one negative. Still 2 negatives, 2 negatives. Okay, 1 positive, 1 negative. So this will take you to 0. All right. I hope you're tracking. Any questions? Understanding scale symmetric random walk. On top of this, actually, let me increase this to maybe 50. My T is here, right? 50 steps, that is between 0 to 1. And what you see is this path. And the final distribution obviously now looks like a normal, because if you increase the number of steps, central limit theorem tells you it will start to look normal. But the variance, it's still contained as 1, because capital T is 1. So the variance of the process would still be 1. Okay, with more number of steps, I can make it look more and more normal distribution. That's all. The variance is not exploding because capital T is fixed. Remember, in the previous example, when we were increasing the number of steps, the variance was increasing. More and more extreme values were likely. Here, that is not the case. Here, you are increasing the number of steps, but the step size also you are controlling. It is getting smaller and smaller and smaller. Overall effect is still always this. All right. So that is scale symmetric random walk. Now, question. Actually, let me not ask the question. If this is desirable, question is, why are you then modeling everything in a discrete fashion? Two values. Why are you doing that? If you want this end result, why not make the step itself take continuous random values? That's the question. Okay. Why are you taking discrete evolution? So in one step, there are only two possible values. And then you are coming up with a walk. And then you are imposing central limit theorem, taking large number of steps, making it look like normal. Why do all that? Why not, why not model the step itself as a continuous random variable, right? For example, if you want this to be your end result, you can make the step also a normal random. And adding a bunch of random normals, which is nothing but what you're doing in the walk, right? You're adding a lot of steps. If each step is a random normal, adding a lot of random normals will be another random normal. I can still retain this final desirable property, but I can work in continuous domain. I can make everything continuous. That way, what will happen? What is the advantage of working in continuous domain? Anybody? Instead of doing things discretely, what is the advantage of working in continuous time domain? Yes, Kavish says can differentiate exactly. The maths becomes a lot easier. Okay, the floodgates of calculus open up. The moment you make anything continuous, right, you can use calculus. You can differentiate, you can integrate, you can do all kinds of things. Okay, so yeah, the floodgates of math will open up. You can write down equations, you can differentiate, you can derive a lot of different things quite naturally. You don't have to deal with this discrete set of values, right? So that's one of the biggest advantage. And also, as Rashid said, it is a little more realistic, because if you really see, right, in one step could mean, let's say, 1 day. Stock price taking two values, that's unrealistic, right? It's better if we can make it more continuous so that it can take any value possible. That is a little more realistic. That is another motivation. So let's do one thing now. Let's go to continuous version of this. Okay, let's go to continuous version, but keep this in mind. This is what we still want. This is very beautiful, because you have a process that see, there is another motivation. See, if you look at this process, I got a process that is normally distributed. The variance is equal to time. That means the more time you allow for the process to evolve, the more uncertain it becomes. And that is a desirable feature. I know that today, if the stock price is $20, the kind of uncertainty that I have after a day is very, very, very small compared to the kind of uncertainty I have after 10 years, right? If you allow 10 years for a stock price to evolve, it could become anything. You have no control. So this is desirable. Variance or the uncertainty grows with time. Okay, so let me stop this. Let's go to continuous version. Other sheets will be a little faster. Now that we understand all the fundamentals. Okay, so this is where the Brownian motion comes into picture. Now look at this. Our step has become, see, in discrete, we write delta. In continuous, we write D. D means differential. Okay. Not trying to be too technical here, but these are some of the very, very, basic things that you need to know about. Our step now looks like this. It can take any value. It is a normal distribution. I'm denoting my step as dw. Okay. Now here is the thing. This is called as Brownian increment. Brownian increment. Increment means step only, right? How much it changed, on a small time interval. That is the step called as Brownian increment. The walk, right, which is the aggregation of all the steps, is called the Brownian motion. Okay, now this is the fundamental entity for modeling. Without this, we cannot proceed. Pricing, risk management, anything. Okay, so yeah, the same setup, right? We have a step and then we have walk. Instead of summation, now we have integration. Nothing to be scared about because in continuous, right, we differentiate, we integrate. That's all we do. Integration is same as summation, right? So our step is a normal distribution. Now look at this. Again, centered at 0, the variance is dt. dt is the time interval, extremely small time interval. In that small time interval, the step that it can take is a normal distribution, mean 0, but the variance is equal to the time interval. And that makes sense. The longer the time interval, the step could be bigger, right? Stock price, $20 right now. If you allow one day, it could be, 21, 19, 23, 16. If you allow a month, it could be 40 or even, close to 0, right? So this makes sense. The variance, the uncertainty is tied to that time interval. Smaller the time interval, smaller the uncertainty, bigger the time interval, bigger the uncertainty. But we are working in infinitesimal, that means very, very, very small time interval dimension. Okay. Okay, dw is this. This is the increment, expectation is 0, variance is dt, as per the definition. Why this is chosen is because if you integrate means basically you are adding lot of these steps together or the increments together. What happens when you add a lot of normal randoms? When you add lot of normal random variables, the end result is also normal. Exactly. Remember, the means get added, the variances also get added, provided the steps or the increments are independent and of course identical. If it's independent, there'll be no covariance. If it is identical,